This is sequential veto bargaining with incomplete information. I'm Nageeb Ali. I'm at Penn State. This is joint work with Navin, Kartik at Columbia and Andreas, Kleiner at Arizona State. So let me tell you what we're doing in this paper. So we're thinking about the process of veto bargaining, which is this process used to understand negotiations that take place over politics, over policies by political organizations. So you can envision a legislature that is sending bills to an executive that can choose to either accept or veto that bill. You can think about executives who are suggesting appointments for, let's say, a Federal Reserve Bank or a Supreme Court to a legislature to confirm or reject such appointments. Or you could think about search committees that put candidates for approval. So here's an image of someone who's not a co-author talking about whether he wants to veto a bill or sign it, and saying that for now he must veto the bill, but he's willing to consider versions of it that are modified. Okay, so what is the canonical model for veto bargaining? So the canonical model comes from a paper by Romer and Rosenthal in 1978, where they think about two players, a proposer and a vetoer, where the proposer is the one who can make offers. A vetoer can either accept or reject offers. And what they're bargaining over is a one-dimensional policy. Okay, and so this is going to be a single take it or leave it model with complete information. So just to make sure to fix ideas, so we've got a status quo in place, which is policy 0, a proposer who would like to have policy 1, and a vetoer that has an ideal policy, which would be policy V, corresponding to the vetoer's preferences. And what do I mean that V is the vetoer's ideal policy? It would be if I could, imagine graphing the utility loss the vetoer has from any other policy. At V, she gets a loss of 0. And at any other policy, she sort of has this sort of negative loss, and it's quite common in this literature to think of either like a linear loss, that's a distance from her ideal point, or a quadratic loss. Okay, so these are the preferences, and in the canonical model, the proposer makes a one-shot, take it or leave it offer. Now, all of us who know game theory know what's going to happen here. The proposer is going to think about what is the vetoer's loss from the status quo prevailing, and is going to propose a policy that makes the vetoer just indifferent between accepting and rejecting the policy. As a result, the vetoer reaps no surplus from accepting this policy, but of course the proposer is able to achieve more than just the status quo. The reason this intuition is very familiar to Rubinstein-like logic. This predates Rubinstein, and one of the reasons political scientists found this fascinating was that even though vetoes are not exercised on the equilibrium path, the vetoer nevertheless has some influence over the eventual outcome. Okay, so this is the sort of the classical model, and what we're going to do in this paper is we're going to re-examine two assumptions within this model. So the first assumption that we're going to examine is the sort of the classical literature assumes that the proposer knows the vetoer's ideal point, and as a result can target the vetoer perfectly. But you could imagine that if the proposer does not know the vetoer's ideal point, they wouldn't be able to target this precisely. The second is that the classical model is really a one-shot model. Either there's a one-shot possibility of proposing this policy and passing it, and if it's vetoed, the game is over, where we're stuck with the status quo. But you could imagine, indeed, as the quote from President Obama suggested in the very beginning, that once a policy is vetoed, there are opportunities for future policies. So you can make proposals even after rejection. Now, you could imagine now that the proposer is making proposals, seeing that these are rejected, and drawing inferences about the vetoer's preferences. Of course, this could also mean that the vetoer would strategically reject proposals today in order to obtain compromises in the future. And this brings us to a sort of a classical post-conjecture question, where if it's the case that the proposer cannot avoid moderating proposals after rejection, is he going to be at the mercy of the vetoer's private information? Okay, so that's the question this paper is going to ask. And what we find is that the post conjecture does not hold in this setting. The proposer is going to be able to benefit from being able to make sequential proposals. And in fact, lack of commitment is not going to hurt the proposer. She's going to be able to achieve his commitment payoff in an equilibrium of the game. Okay, so these are the results that we have. The first is that the commitment payoff is achievable when players are patient. Namely, for patient players, there exists an equilibrium where the proposer's payoff is identical to his Stackelberg payoff, namely that which he gets from committing to a strategy in the dynamic game. This is also going to be the payoff, the best payoff he could get from an optimal static stochastic mechanism. The second punchline from our analysis is that this proposal is going to exploit something that we call leapfrogging, where instead of starting off with an aggressive proposal that the proposer likes and moderating after rejection, the proposer might actually start off with a very low proposal and then later make proposals that are closer to the proposer's ideal point. And this owes to the single-peaked preferences that are at the core of our analysis and is unlike the skimming equilibria that we typically think of in durable good monopoly. There could be multiple equilibria, so there exists an equilibrium in which the proposer obtains his commitment payoff. There also exists equilibria with Gaussian dynamics. And so this highlights the implications and importance of norms in legislative negotiations. Okay, so those are the results. What I want to do is I want to sort of tell you a little bit about the model and then give you a simple example to elucidate the core ideas here. So here's the model. So at each of, discretely many times, the proposer can make a proposal that's somewhere on the real line that the vetoer can accept or reject. The game is going to end when the vetoer accepts a proposal. If it's the case, I guess does this cursor work? Yes. If it's the case that they reach agreement in period t, then the proposer is just going to get his discounted expected utility from the proposal passing. And the vetoer is ditto for the vetoer, where the vetoer's utility depends upon the vetoer's private type. So the way in which we think about these payoffs is before an agreement is reached, each of the proposer and the vetoer is going to obtain flow utility from the status quo. And so you can always normalize that utility to be 0. After agreement is reached, they're going to receive flow utility from the agreed upon policy. And so you could just measure this as the utility gain that they have over the status quo. Okay, so these are the payoffs. Importantly, these payoffs, their preferences are single-peaked. So the proposer has an ideal point, which is 1. And the vetoer has an ideal point, which is V, which is her type, which is private information. And you could just think of this as being a quadratic loss with respect to that, or a linear loss. These are the examples we usually have in mind. Okay, and we're going to study perfect Bayesian equilibria of this game. So that's the model. Let me give you a two-type example to sort of highlight how the logic of this analysis works and what we see in leapfrogging. Cool. Okay, so once again, here I have the proposer's utility. This is a typo, there shouldn't be a V here. The proposer's utility from an action is just the linear loss with respect to the ideal point of 1. I've just got this other constant here to normalize the utility so that the utility from the status quo is 0. Ditto for the vetoer, it's just a linear loss with respect to an ideal policy of V. And really, you can take my word for it that the interesting case to look at is going to be the one here, where the vetoer has 2 types, low and high, where the interesting case for the 2-type model, where the low type's ideal policy is less than 1/2. The high type's ideal policy is greater than 1/2, less than 2L, which is less than 1. And let me elaborate on why this is the interesting case. So what would happen if the proposer knew the vetoer's type? If the proposer knew that the vetoer was the low type, the proposer would extract full surplus from the vetoer, make a proposal of 2L. The vetoer would be just indifferent between accepting and rejecting, and that's what the proposer would be able to get from the low type. On the other hand, if the vetoer were of the high type, the vetoer would retain some surplus. The proposer would propose her favorite policy, policy 1, and the high type would be willing to accept. Okay. So under complete information, the proposer would obtain a policy of 1 from the high type and a policy of 2L from the low type. The challenge is that if types are private information, this is going to violate incentive compatibility for the high type, because the high type prefers the allocation that the low type receives over the allocation that the high type receives. Okay, so the IC constraints wouldn't be satisfied because the height 2L is closer to H than 1. All right. So what do you do? So for a moment, first let's think about what you would do with a static mechanism, and then I'll elaborate on what we're going to do in equilibria. So with a static mechanism, you're going to really have two choices. First choice is to say, look, if the high type is not sufficiently likely ex ante, proposer is going to say, I may as well just give up on trying to extract this surplus from the high type of extracting a policy of 1. I'm just going to pool on 2L. I'm just going to get 2L from both the low and the high type, if the high type is sufficiently unlikely. On the other hand, if the high type is sufficiently likely, then what the proposer is going to do is going to say, look, to try to get the high type, to get a policy of 1 from the high type, I'm going to distort the allocation from the low type, get a policy of A star that makes the high type just indifferent between A star and 1. And that this is going to be the optimal separating menu. So the proposer is going to just can delegate the choice to the vetoer and says, look, you have two choices, either A star or 1. The low type of the vetoer is going to take A star. The high type is going to take policy 1. So this is what you would do if the proposer could, this is what the proposer could do if he could commit to a mechanism. Is going to either choose between pooling or separating. And the main question for us is whether the proposer can achieve the separating outcome in an equilibrium of the game. So this goes exactly contrary to the logic of Gaussian logic, where we know the proposer typically struggles with separating types of the buyer. Okay, cool. So you might say, how could you try to implement this in an equilibrium of the game? Well, you could say, you know what, let's try the standard skimming recipe, where what the proposer does is he begins with a proposal of 1, which is putatively meant to be accepted by the high type. If it's rejected, then he moderates his proposal and proposes A star, which would be accepted by the low type. And perhaps you do this modulo some kind of discounting adjustments. I'm being a bit sloppy here. But this would be the standard skimming recipe, and this standard skimming recipe is going to have a challenge. Namely, it's going to fail sequential rationality if it is indeed the case that the high type would have accepted a policy of 1. Upon rejection, the proposer knows that it must be the low type. But from a low type, the proposer would want to obtain not A star, would want to obtain 2L, in which case it would have an incentive to propose 2L following the rejection of that first offer. Of course, the vetoer would anticipate this, and now a vetoer that is of the high type would not want to accept an offer of 1. It would want to reject it so as to obtain an offer of 2L in the future. Okay, so this is why skimming wouldn't be able to obtain this outcome. Instead, what could work? And this is what we think of as the leapfrogging solution. So what the proposer does here is first the proposer proposes A star. And this is meant to be accepted only by the low type. After that proposal is accepted, after that proposal is made, and if it has been rejected, then the proposer knows that it must be the high type. And now it credibly just offers a proposal of 1 forever after, in every period. And so then the high type accepts in period 2. What's the key idea here? The key idea is that by first securing agreement with the low type, sequential rationality no longer impels the proposer to moderate his proposal should the high type reject. To say differently, once the first proposal has been made of A star and it's rejected, then the proposer knows that he's facing the high type. And so there's nothing the vetoer can do by rejecting proposals to induce future concessions. And this is why leapfrogging works. This owes very much to the single-peaked vetoer preferences here. This would be, in monopoly pricing, this would be completely futile. This would be, if I'm not entirely sure about what someone's value is for a good, well, all types want things at lower prices. So charging a low price early is not going to help me clear the market. By contrast, what's happening here is by offering a low proposal first, the proposer is able to clear the market, quote unquote, of the low types so that he can credibly go after the high types thereafter. Okay, good. So that's the logic of leapfrogging. Now, leapfrogging need not actually occur on path. Because of discounting, the proposer might have an incentive to target the high type first, but it's always an option available to the proposer. So you can have a very succinct proof to highlight that if an equilibrium exists, there exists an equilibrium in which the proposer is able to obtain this payoff. Now, in addition, one is able to also construct an equilibrium where this happens, but that construction is somewhat subtle. And in that construction, leapfrogging, as I've presented it, happens only for moderate priors. In this particular form, one has to adjust it. But nevertheless, a proposer still obtains this high benchmark payoff from being able to commit. OK. So that wraps up the example. That I've shown you that there's sort of this thing that you could use called leapfrogging, with which the proposer is able to attain high payoffs that goes contrary to the standard Gaussian logic. There may be two concerns you have about this example, or two concerns we had about this example. One concern would be, is this necessarily the best equilibrium? Could the proposer do even better? And you might ask, in this example, you might ask, well, why is this the optimal delegation payoff the right benchmark? Is this indeed the optimal mechanism among all stochastic mechanisms? Both of these concerns are things we address by the general analysis. So what we show in the general analysis, I'm just going to flash to our result, is that under a condition on what the optimal mechanism is, and assuming an equilibrium exists, we can show that there exists an equilibrium with the proposer obtaining the payoff that he would obtain if he were able to commit to his optimal dynamic strategy. So in some ways, the concern about whether this is the right kind of commitment is addressed. And indeed, there's nothing you could do that's better than this. This is indeed the proposer obtaining the commitment payoff. Now, proving this result has a number of technical and substantive assumptions. Technical assumption is that we're able to be very general about the proposer's utility function. But for the vetoer's utility function, we actually have to specialize to the class of quadratic loss. And the reason we need to do this is we need to ensure some kind of single crossing property over lotteries. So that's one technical assumption. A second substantive assumption that we need to make is that, let me go here, yes. A second substantive assumption that we need to make is we need to sort of be able to understand what it is that corresponds to the proposer's static optimal mechanism. And so an assumption that we make is that the optimal static mechanism is an interval delegation set. You can find conditions on primitives under which this is indeed optimal. And we show that whenever the static optimal mechanism is an interval delegation set, it is indeed the case that you can achieve this in an equilibrium of the game. OK, so let me wrap up. So what this paper does is it looks at bilateral bargaining over policy, where we have single peak preferences and the proposer is uncertain of the vetoer's ideal point. There are 3 takeaways of this, and I focused on 2 of these. The first is leapfrogging behavior, which does not arise under standard Gaussian environments. The second is a fundamentally non-Gaussian result that the commitment payoff can indeed be achieved. The third takeaway is that other equilibria coexist. In fact, there exists also, under some conditions, a Gaussian equilibrium in which the proposer obtains low payoff, and hence this suggests that norms can matter in legislative organizations and institutions, which is something, of course, the political economy literature is also interested in. OK, that's all I have.
Any questions from the audience?
Given multiple equilibria, what would happen if you have a finite horizon and with some kind of backward induction? Would it select one of the equilibria?
Great. So actually, for many of the contexts that we've looked at, our equilibrium remains an equilibrium of the finite horizon. But there have been cases where we have not been able to support the skimming equilibrium. So from that perspective, the analysis seems, this sort of leapfrogging solution seems fairly robust. Yeah.
there's a discrete finite set of types they could conceivably be. And my first intuition as to when somebody's uncertain about Vito's position in this would be something where there's a continuous distribution over the Vitor's positions, where it's like single peak split, could be a little bit to the left, could be a little bit to the right.
That's right.
When you went for this specific two-type version, was the motivation about tractability, and what was it?
Oh, excellent. Okay, so the motivation for me showing you the two-type version is this is what I can get through in 15 minutes. My general analysis, I went through the slide very quickly. The general analysis is with types that are from some distribution with continuous support and a density. So the example of two types is simply for concreteness to fix ideas. Perfect, yeah, thank you. Thank you for asking that question. Yeah.
Okay, then let's take all speakers again.